Hi, my name is Mark Weitzman. Welcome back to another video on topics in theoretical physics. Today I'm going to do a problem in relativistic quantum mechanics. And this is a problem from chapter 2, problem 4 of a famous textbook called Relativistic Quantum Mechanics by Bjorken and Drell. And here's my copy of this book. It's so old the title is washed off, but it was one of the earliest and best books on Feynman diagrams. It was published in 1964, and believe it or not, when I was at Caltech in 1984, they were still using it for their quantum field theory course. So nowadays, there are much better books on quantum field theory. But if you want a book on just Feynman diagrams and how to calculate them and the Dirac equation and the Klein-Gordon equation, Bjorken and Drell is an excellent book. So I want to start out just by saying what their problem is. We have to find, so we want to show that there exists 4 times 4 matrices, gamma u, and as the standard convention in Bjorken and Drell, u equals 0, 1, 2, 3, time, 3 spatials. And we want it such that the real part of gamma u alpha beta, these are the indices, is equal to 0. In other words, we want the gammas to be purely imaginary, and yet we still want them to satisfy the standard, I'll write it this way, anti-commutation relations for the Dirac matrices. Remember, G mu mu is the metric, Bjorken and Drell convention is a 1 minus 1 minus 1 minus 1 convention. Now, so I'll start by reviewing the standard Dirac equation. At least there's a lot of different representations. Most quantum field theory books today use the chiral representation, but Bjorken and Drell used the representation that was probably closest to Dirac's original representation. It's called the energy representation, and in it it's very easy to see what the small, the upper parts correspond to the large parts of the wave equation, and the lower parts of a spinor correspond to the antiparticles or the small particles when we're at normal energies. Anyway, the celebrated Dirac equation is I gamma u partial with respect to x mu minus m psi equals 0. And the standard representation that Bjorken and Drell use is gamma 0 is equal to, use a different pen, 1, 0, 0 minus 1, and gamma I is equal to 0 sigma I minus sigma I and 0. And the sigma I are the standard Pauli matrices. I'll write them again. Sigma 1 is equal to 0, 1, 1, 0. Sigma 2 is equal to 0 I minus I 0. And sigma 3 is equal to 1 minus 1, 0, 0. So if you look at this representation, you can see that gamma 0 is going to be all real numbers, gamma 1 is going to be all real numbers, and gamma 3 is going to be all real numbers, but gamma 2 is going to be imaginary. So the equation if we can get the real of this to be 0, if we can get the gammas to be all imaginary, we're multiplying by an imaginary part, so this whole equation becomes real. And that's what the problem wants to show. And this has applications to things like Majorana fermions and everything. So it's not a hard exercise. Actually, it's very easy. And let me just show you what to do. First of all, the first thing we're going to try is, let's just try a unitary transformation, like psi prime of x equal u psi of x. U is u dagger, u equals u dagger equals 1. So u is unitary. And if we do that and substitute in the Dirac equation, then we're going to get, very simply, I gamma u partial with respect to x mu minus m. Psi of x is u multiplying it by u dagger here. U dagger psi prime of x is equal to 0. And then if we multiply this equation by u, and since it's unitary, we don't have to worry about the I. So we're going to get I u gamma u u dagger partial with respect to xu minus m u dagger. This whole thing multiplied by psi prime equals 0. So u dagger is 1, and we end up with I gamma u partial with respect to x mu minus m psi prime of x equals 0, and where the gamma u is equal to u gamma u dagger. So this is the standard way a matrix transforms if we perform a transformation on the spinor or the vector. So we have to find a u such that gamma u's are going to all be pure imaginary. Now, one of the advantages of using a unitary transformation is that this will preserve the commutation relations, because we can see the anti-commutator of gamma u comma gamma nu is equal to gamma mu gamma nu plus gamma nu gamma u, which is equal to u gamma u dagger u gamma nu u dagger plus plus the same thing, u gamma nu gamma I don't know why I did that. Okay, u gamma u dagger u gamma nu u dagger u gamma u dagger, and then using the unitary relationship, this is just equal to u times gamma u gamma nu plus gamma nu gamma u dagger, which is equal to u 2 g mu nu u dagger, which is equal to 2 g mu nu. So we'll preserve the commutation relations if we do a unitary transformation. Now we just have to find one where we can make it real. Now, since gamma 2 is pure imaginary, that might be our first choice for u. We'd like to, because we don't want to change gamma 2. Gamma 2 is already, this is pure imaginary. So we want to do a transformation which leaves gamma 2 alone. And if we use u equal gamma 2, that will work. The problem is it won't change the complex or real or imaginary character of any of the other matrices, because if you take gamma u star, let's say you use u equal gamma 2. So you try that. That was the first thing I tried. And then you get gamma u star is equal to gamma 2 star, gamma u star, and then this is going to be gamma 2 dagger star. And each of these just gets a -1. Gamma 2 star is going to be -1 gamma 2. We're going to get gamma mu star. And then gamma 2 dagger star is just gamma 2 transpose, which is just a minus sign again. So we get minus gamma 2. So this ends up being gamma 2, gamma mu star, gamma 2. Now, if mu is 0, 1, or 3, these matrices are pure real numbers. So gamma mu star equals gamma mu. And all we've established is that our new matrices, the complex part of it is equal to the matrix. So this is going to end up being equal to gamma mu. That means that gamma is real, and we want gamma to be pure imaginary. So this doesn't work. But it's close. Now I'm going to show you what does work. So we've established if we use a unitary transformation, the commutation relations will continue to hold. So the next thing I tried was try u equal 1 plus gamma 2 over the square root of 2. So first thing, let's check that this is unitary. So u dagger is equal to 1 plus gamma 2 dagger over the square root of 2. And if you look at the gamma 2 matrices and take the dagger, it's just a minus sign. So this is equal to 1 minus gamma 2 over the square root of 2. Basically, the sigmas are Hermitian, so when you transpose and take the Hermitian conjugate of the inner matrices, you just get them, it just ends up being minus. So now let's just verify u dagger equals 1 plus gamma 2 over the square root of 2 times 1 minus gamma 2 over the square root of 2. This is equal to over 2. Then you get 1 minus gamma 2 plus gamma 2 minus gamma 2 squared. This cancels. You can verify that gamma 2 squared equals -1. So this is equal to 1, and our u is unitary, so that's good. Now let's see if it does what we want it to do. So first, let's try and calculate gamma 2. Well, gamma 2 is just equal to u gamma 2 u dagger. And we know that gamma 2 commutes with the real number and it commutes with itself. So it commutes with u. So this is just equal to gamma 2 u dagger, which is equal to gamma 2. which is good because gamma 2 was pure imaginary, so we haven't changed it, and we still have the pure imaginary that we want. Now let's do gamma 0, 1, or 3. So this is equal to u, gamma 0, comma 1, comma 3, u dagger. So this is going to be equal to 1/2 1 so let me write it out. 1 plus gamma 2, gamma 0, 1, 3, 1 minus gamma 2. Now we know that all of the gammas anti-commute with each other. This is the, I didn't write it down, this commutation relationship, or gamma u, gamma nu equals 2 g mu nu. So when mu is unequal to nu, this is the anti-commutator, this is 0, so they anti-commute. So I can bring this to the left, so I get 1/2, you know what, I'm going to bring it to the right. So I'm going to get 1/2, 1 plus gamma 2 times 1 plus gamma 2, because it commutes with the 1, but it anti-commutes with the gamma 2, times gamma 0, 1, 3. Now let's just multiply this out. I have 1/2, 1 plus gamma 2 plus gamma 2 plus gamma 2 squared. And again, you'll find out that gamma 2 squared, we already know, gamma 2 squared is minus 1, so this cancels this. And so we just get, well, that times gamma 0, comma 1, comma 3. So we just end up getting gamma 2, gamma 0, comma 1, comma 3. Okay. Now the question is this a pure imaginary matrix? And it's easy to see that obviously it is, because this is pure imaginary and these are all pure real. But, you know, if we were to take the complex conjugate of 0, 1, 3, we would get gamma 2 star, gamma 0, 1, 3 star. These are all real, and this is pure imaginary. So we end up getting minus gamma 2, gamma 0, 1, 3. And that's what we want. So this is pure imaginary. Okay, so that solves the problem. Like I said, it's not very hard. Where you come up with the 1 plus gamma 2, I don't know, that's a common transformation, but it should be obvious that you need the gamma 2 in there, and since the gamma 2 itself doesn't work, the only other thing you could do is like try and add a real number. So I'll see you tomorrow in the next video. Thank you very much.